Now let's go on with the second type of modeling we will be using in this module, which is the electrical model. To do that, let us first discuss about electrical systems. We will be using three components representing electrical systems. First is the capacitor, and this is the voltage across the capacitor. It is equal to 1 over its capacitance, the integral of the current dt. And by the way, the Laplace transform of integration will just be equal to 1 over s. So if we convert this equation into its equivalent Laplace transform and get the impedance, which will be the ratio of the voltage and the current, the impedance of a capacitor will just be equal to 1 over Cs. Next is a resistor, and we all know the voltage across a resistor using Ohm's law is just equal to R times the current. Converting this into Laplace and solving for the impedance, we will get the impedance of a resistor to simply be equal to R. And the third is an inductor, and the voltage across an inductor will be equal to its inductance times the derivative of the current through the inductor. And the impedance will be equal to Ls. Now let's go to a numerical problem to illustrate those three components. Write the modeling equation and the transfer function I of s over E of s and V of s over E of s for the given electrical system below. In electrical systems, the input can either be voltage and current as well as the output. So in this example, our output will be in terms of current for the first transfer function and in terms of voltage for the second transfer function. So this is our given electrical circuit where we have a series connection of a capacitor, a resistor, and an inductor. And the output voltage is taken across the resistor. So first, let's have the transfer function as a ratio of the current and the input voltage E. So this is the given circuit, and using Kirchhoff's voltage law around this loop, where the loop current is labeled as I of t, then the sum of all voltage source is equal to the sum of all the voltage drop around the loop by Kirchhoff's voltage law. And substituting the values of the voltage across the capacitor, across a resistor, and across an inductor, we will get this equation. And since we would like to get the transfer function, which is in Laplace transform, we have to convert this into its equivalent Laplace transform, remembering that integration will be equal to 1 over s. So this voltage across the capacitor will have its Laplace transform equivalent to this term. This is the voltage across the resistor, this term, and the voltage across the inductor in terms of Laplace transform is this term. And we have three terms, and we can put them in a single fraction where our common denominator is Cs. So this will be the equation when we put these terms in a single fraction. And if you will notice, we have a common factor in each of these three terms, which is I of s. We can factor that out, and now we are ready to determine the transfer function, which is just equal to the ratio of the current I of s and the voltage C of s, which will be equal to the reciprocal of this term. To represent this transfer function into its equivalent block diagram showing the output current Is and the input voltage Cs, then this is the transfer function of this electrical circuit. If you are given the values of the capacitance, the resistance, and the inductance, then you will simply substitute them in this equation. Now let's get the second transfer function, which is in terms of the output voltage across the resistor. So again, this is our circuit, and the voltage, the output voltage, will be taken across the resistor. Previously, we have this around the loop, followed by the Laplace transform of each of these terms, and we can now factor the common current I of S, where we have this equation. We do not want I of S, instead we want V of S. So to do that, let us get the equivalent of V of t. V of t is just equal to the resistor times the current I of t. Converting this into its Laplace transform, we have V out of S is equal to R I of S, and solving for I of S, it will be V out of S over R, and this value can be replaced by this value, so we have this equation. Now we were able to eliminate I of S, and we have introduced the variable V out, which is what we would like to have in our transfer function. So we have R in the denominator. We distribute this R to the three terms, so we will have this, and we can combine this in a single fraction where our least common denominator is RCS, and that will result into this fraction. And if you will notice, we now have the output voltage and the input voltage E here, so we can just get the ratio, which is the transfer function. It will now be equal to the reciprocal of this, so we have this RCS all over LCS squared plus RCS plus 1 as the transfer function of this circuit in terms of V out and E of t, and this will be the equivalent block diagram representing the electrical circuit given. Let's go on to another example. This time we have a two-loop electrical circuit. The problem is, write the modeling equation, that means the differential equation, and the transfer function for the given electrical system in terms of I2 of S and V of S. And the values of the resistors, the inductor, and the capacitor are given, and these are arbitrary values, and we will be using 1 ohm, 1 Henry, and 1 farad for simplicity of the solution of this problem. So first, by the way, we would like to determine the transfer function I2 of S over V of S, and this is our circuit. Our loop currents are I1 of t, and in the second loop we have I2 of t. So to determine the equations, we will use loop or mesh analysis. So we will determine the equation in each loop. So the first loop, if we go around this loop, we will have Vt as the voltage source, and the voltage across the R1 will be a drop, and the voltage across the inductor will also be a voltage drop, and the voltage across the inductor, it will be equal to the inductance times the derivative of the difference in the current through the inductor. When we are in loop 1, it will be I1 minus I2. So this can be exploded further as the derivative of each of the currents I1 and I2, and we can now convert this into their equivalent Laplace, knowing that derivative is just equal to S. And if we distribute this one inside the bracket, then we will have this as the expansion of loop 1. Please notice that the values of R1 and L have been replaced in the equation, so this is we have a common factor I1 of S in two terms. We can factor that out, transpose it to the right side, so the negative becomes positive, and this positive, when it is transposed to the right side, becomes negative, and this will now be our equation. Now let's go to loop 2. If we inspect loop 2, this is just a summation of all voltage drops. So it is the voltage drop across the inductor minus the voltage drop across the resistor and the voltage drop across the capacitor. If we are in loop 2, we know that the current through the inductor will now be I2 of t minus I1 of t. So substituting the values of L and R, we will have this, as well as the value of C. We will have this equation, and distributing -1 inside, we will get this equation. Then we just convert this into their equivalent Laplace, so the derivative will be equal to S, and I2 of t will become I2 of S, followed by this term and this term, and the integration is 1 over S, so it will be 1 over S. I2 of S will be equal to 0. If you will notice, we have three terms with I2 of S, and they are all negative. This term, and this term are all negative. We can factor out the negative in I2 of S, so we will have this form, and we have also I1 of S, which is positive, and all of this is equal to 0. And let us call this our equation number 2. Since we have two equations and two unknowns, we are going to solve them using different methods, but again we will be using determinant and using Cramer's rule. We can have I1 of t as the output, or we can have I2 of t, or in this case I2 of S, because they are already in their Laplace transform. We can have this as our output, or I1 of S as the output. But since we are using single input, single output analysis in this system, in this module, we will be using I2 as our output. So to do that, we will just substitute the constant on the second column of this matrix A divided by the determinant of matrix A. Matrix A, by the way, is the matrix that has been discussed in the previous video. So to get the determinant, we will have this in the numerator and this in the denominator. Again, if we look at the numerator, it's negative. We can make this positive by multiplying negative 1 in the numerator as well as -1 in the denominator, which will make this positive. This will become positive, and this becomes negative. So here it is. So further, we can still simplify this. We see that this is a fraction, mixed fraction, so we can put this in a single fraction with the common denominator as S. So we have this. Still, we can put all the denominator in a single fraction, and the common denominator is S. So we will have this as the simplified single fraction of the denominator, and the S here can now go up, which will make the numerator S squared. We can expand this, then subtract S cubed, and we will get this as the simplified transfer function of the given circuit in terms of I2 of S and V of S. And we can represent this in a block diagram showing the output I2 of S and the input V of S, and here is the equivalent transfer function.